we are after is we want to describe our velocity at an instant. So at a particular point in time. Let's think back to our car example, where we had time over there, and we had x in meters over there, and the position of the car changed with respect to a point of reference, say like that. So this is again just how the position changes with time. Now let's say we want to know at that point, so let's call this point T1, how fast is the car moving at this point? So we can start to get an approximation for this. So, well, let's say we take this point and that point, right? And we know the slope of a line passing through these points gives me the average velocity between that interval. So let's call that T initial, T final. So we know the slope of this line. Remember, the slope is the change in the vertical axis. So in this case, delta x, divided by the change on the horizontal axis. In this case, it's delta t. So that's x final minus x initial, where that would be x initial, and that would be x final, divided by t final minus t initial. Right? And we know we've already defined this quantity. This is then the average velocity during the time interval delta t is equals to t final minus t initial. Now, this is on average what our velocity was during that time interval. If we make this interval smaller, so let's say we choose rather 2 points over there, we get a different straight line. And if we make this interval smaller and smaller, so making this interval smaller and smaller gives a better approximation of the velocity at that particular time t1. Right, so we can, at least we're one step further from where we were a few minutes ago. At least now we have a method with which we can approximate the velocity at an instant. We just make the time interval over which we measure the change in position smaller and smaller and smaller. Now, how small can it be? So those of you who have done some mathematics, so, you had an answer? Goes towards zero. What does goes towards zero mean in everyday language? Yes. That's it. So you make this as small as possible, this interval. So you make that interval go as small as possible without it actually becoming zero, because we can't divide by zero. Right? So if we choose a time interval that is as small as it can be without being zero, we actually do get the velocity at a specific point in time. So the fancy way to write this down is to say our velocity at a particular time is equals to the limit of where we make this time interval go as small as it can be without being zero. That's just a short way of writing it, of the change in position in that small little time interval. And this we will define as the instantaneous velocity. Now, this looks rather complicated because you might not have seen this before, or you might not be familiar with this, but it's got a very simple graphical interpretation. If I want to know what is the velocity over here, I know if I draw a line, a straight line, that just touches the curve just at that point, one single point, the slope of this line is equals to the instantaneous velocity. So in mathematics, you will learn how to calculate things like this. We're not going to go into that too much here. What I want you to remember is that on a graph, that instantaneous velocity is equal to the slope of a line that just touches the graph at that point. You can think that is the natural thing which we converge to if we make this interval small enough. If we make this interval smaller and smaller and smaller, these lines move down, down, down to right where they just touch that point where we want the velocity. And the slope of that line gives me the velocity at a particular instant. Now, there is a fancy name for this. This is called the derivative of the position versus time graph. Now, you will learn in mathematics what a derivative exactly is, how to calculate it in different cases. Here, I just want you to know that the derivative of this function, position versus time, what it physically means is it's the slope of a line just touching this function x of t in one point. So for now, that's the only thing you need to know about derivatives for physics. You will learn more of them in mathematics, and then while you're busy with that, when we come back to these things, you'll be more adept at handling them. But an interesting example is, so I just want to show you one way of calculating the derivative, a very simple method. So how to calculate a derivative. Now, I'm just going to show you one. It's a simple formula that you can just remember. Again, in mathematics, you will derive exactly why this is so. Let's say you've got a function. Let's forget physics. Let's say you've got a function y is equals to ax squared plus bx plus a constant. Right? So it's a parabola. It's got x squared term in there. Now, if I want to calculate its first derivative, the first thing I do is I write out just explicitly what the powers of x are. Now remember, anything to the power 0 is just equals 1. So I haven't changed anything. I've just put in some extra, I've just made clear things that we usually assume are there. And now if I want to calculate the derivative, I take that number and I place it in front. I take that number and I place it in front. I take that number and I place it in front. And I subtract 1 from each of those. So the first derivative of y is I take that number, put it in front. So I'm just going to denote the first derivative of y with the little accent. So if I place the 2 in front, I get 2 times a times x. And if I place the 1 in front, so remember I've subtracted 1 from the 2 there, so there's now a little 1 over there, so x to the power 1 plus a b, because if I subtract 1 there, I get x to the power 0. If I put the 0 in front, 0 times anything is 0, so I don't have any term over there. And I can write this more simply as just 2 times ax plus b. And this is just the equation for a straight line. Remember, a is a constant anyway. So if I have a parabola and I take the first derivative, I get a straight line. So what does this mean? So this function gives the slope of our parabola at point x. And we can calculate the derivative of this as well. We just follow the same formula to calculate its derivative. I say that's x to the 1, that's x to the 0. To calculate its derivative, I put that in front, subtract 1, subtract 1. So the second derivative, if I do the same process all over again, gives me m, x to the power 0 is 1. If I take a 0 down there, it is 0 anyway, so what I end up with is a constant. So you can just, if you can just remember this purely as a given, how to calculate the derivative of a simple function of x, it's fine for now. As I say in mathematics, you will learn how to do this properly in a more rigorous form. What I want to show you is there's a very nice graphical interpretation of this. So let's now say we've got y as a function of x, and we said it's a parabola, so let's say it looks something like that. So we've got y is equals to ax squared plus bx plus a constant. Then we said the first derivative, what that tells me is if I want to figure out what is the slope of this curve over here at that value of x, or the slope of this curve at that value of x, or the slope of this curve at that value of x, the values of these slopes is given by the first derivative. So I can plot the first derivative as a function of x, and what I find is it is a straight line. So I go from a parabola to a straight line. If I calculate the first derivative. Now, does the slope of a straight line change or not? Not at all. It's constant. So, will you agree with me? The slope of this line is the same there, 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 there. So, if I want to plot the slope of this straight line as a function of x, it's the same value everywhere. So, it must be the same there, the same there, the same there, the same there, the same there. So, the slope of this line increases with increasing x. That's just what the straight line does. Its magnitude increases with increasing x. The straight line has got a constant slope, so everywhere the slope is the same. So that gives me a constant. So the slope of the straight line is the same everywhere. So if I plot the slope of the straight line for all values of x, I must get the same value. So from a straight line, I basically go to a constant. Now, if I follow this reasoning, but instead of just a function y of x, I start with the position as a function of time. And let's assume the position changes like a parabola. So all that this means is you're going faster and faster and faster and faster. So in a certain time interval, you change your position by a certain amount. In a time interval later of the same size, your position has changed by a little bit more. So it means with every set time interval, you change your position by more and more and more. So you're going faster and faster and faster. Now we said that if I've got a parabola and I want to figure out what the slope is at different points, I must calculate its derivative. I know that that will be some sort of straight line. But I also know that the slope of a line passing through that point, that slope, is equals to the instantaneous velocity. So if I want to plot the slope of this curve for different values of time, I get this, and this then has to be the velocity as a function of time. Now, let's look at this. So what this curve is telling me is, here, let's call this at some initial time. There I've got some final time. Here I'm moving at some initial velocity. So let's think of an example where you're driving to Durban and you get on the highway and initially you move at 60 kilometers an hour. As you get on the highway, you have this velocity of 60 kilometers an hour east. We must always have a direction. And 20 seconds later, you are up to speed. You're at the full allowed legal 120 kilometers an hour. Unlike certain singers and politicians who decide to stick to the speed limit. So clearly your velocity is also increasing with time. So not only do you change your position at every instant, your velocity is also changing with time. So there's a certain rate at which you are speeding up. So there's a rate at which you gain velocity. And this rate has got a name. We call this acceleration. So you need to, yes?
Excuse me. When you're trying to work out the instantaneous velocity, so you've worked out the derivative, couldn't you just substitute the x value in?
We're going to do a special case. If you know the position as a function of time, so you can write down position x is equals to some sort of function of time. If you just calculate the first derivative of that, and you know how to do that, you get a function giving you the velocity at all times. If you calculate the derivative again, you get the acceleration at all times. So yes, if you know the function beforehand, you can do it. What we're going to look at in a minute or two is a very special case where we know kind of the reverse. The only thing we know is that the acceleration is constant. And then we can calculate the velocity and the position at a certain time. But the first prize would be to know the position at all points in time, because from that you can really get all the information you need. It's less restrictive than the special case we're going to do a bit later. So, as I said, we call this rate acceleration. Now, similar to what we had with velocity, being a rate at which we change position, we now have a rate at which we change our velocity. If this graph were to be steeper, so let's say I accelerated to 120 kilometers an hour in a shorter amount of time, it means I've got the same change in velocity in a shorter amount of time, which means I had to gain velocity quicker. So the steeper this line is going to be, the larger my acceleration will be. So larger slope implies larger acceleration. And like we did for velocity, we can define an average acceleration as just being now a change in velocity divided by a change in time. So it's my velocity after some time minus my velocity before that time divided by the time interval itself. Right, that's an average acceleration. Again, this has got a direction. If I am driving to Durban and I want to get there quicker, I have to gain velocity eastwards. I must move quicker and quicker eastwards towards Durban. If I hit the brakes, I'm moving slower and slower and slower towards Durban. So it's almost as if I am losing velocity in the opposite direction. So acceleration can also have a direction. It tells you either you're gaining velocity in a certain direction or you're losing velocity in that same direction. So this has got a magnitude and a direction. And like we did again with the velocity, we can define an instantaneous acceleration. So the acceleration at an instant as just the average acceleration, but again where we make this time interval as small as it can be without being zero. So that's how we define instantaneous acceleration. And for the case of this graph that I've shown here, this, even though this looks pretty complicated, the acceleration becomes pretty simple. Because if the acceleration is the slope of this line, a straight line has got a constant slope everywhere. So in this very specific case, the acceleration as a function of time would just be constant. So if my velocity changes linearly in time, it means I'm accelerating at a constant rate. So let me just write that down because it's late in the afternoon. So if the velocity changes linearly with time, that just means the velocity, if I plot the velocity of the car as a function of time, I get a straight line. then it means the acceleration is constant. And an interesting thing about constant accelerations is, let's say this is then my acceleration. If I were to look, let's say, at this time, t1, I find my acceleration is equals to a. If I look at this time, t2, I find my acceleration is exactly the same. If I were to measure my acceleration over any interval, so I want to figure out my average acceleration, I were to get that it is also just equals to the same value. So if the acceleration is constant, we have got that the instantaneous acceleration at any point is equals to the average acceleration between any two intervals, or between any 2 points in time. So constant accelerations, we will see in a second, is a very simple example to look at, and one that is pretty useful. I think we can just take a 3-minute break. I just need to catch my breath. I think you also want to catch yours, and then we'll just finish off.